Okay, let me come back to the sinusoidal again. Right? So let's say I have this sine function, right? Sine wave, right? So how can I store this data? Store this sine wave. I have to take sample, right? I cannot store every point, right? So how do we do the sampling, right? So I have to do a sampling at this point, and this point, and this point, this point, this point, this one, for example, right? Then I save the data into my microprocessor. So now the question you may ask is, how many samples is sufficient to represent my sine wave? Let's say for this case, right? For this case, my one cycle is this one, right? For sine wave, it's from here to here. Right? It's 4 points sufficient. Yeah, do I need more? So this is the question you need to ask, right? How to take samples? Basically, you cannot. Of course, I mean the ideal case you want to see all the points here, right? All the points, everything, but it's impossible. Right? So now the question is, how many data points? What is the minimum data points you need to save the sine wave? So this is something we are talking about. Okay, so according to the sampling theorem, right? So there is a very famous theorem called Shannon. Shannon actually got Nobel Prize. So the Shannon's sampling theorem basically tells you, right, a signal must be sampled, right, is a frequency at least twice the maximum frequency of the signal itself. Right? What it means is, let's say you have the signal, right, which is sampled at 48 kilohertz, right? So that means your Nyquist limit, right, is 24. Okay, so what is the meaning of Nyquist limit, right? Nyquist limit basically is the half of the sampling frequency. Right? Okay, so 48 kilohertz, right, actually is a very common sampling frequency for our voice, for our human voice. So let me ask you, right, what is the frequency range for our voice? Our voice has a frequency, right? What is the frequency range for the voice? The range actually is from about 200 Hz to 20 kilohertz. 20 kilohertz. Okay. So that means 20 kilohertz, right? Yeah. So that means what? That means according to Shannon's sampling theorem, right? So the sampling frequency for our voice, right, minimum need to be 2 times of it. This is the Shannon's sampling theorem tells you, right? So the minimum actually is 40 kilohertz, right? 40 kilohertz. But then you need to have some allowance, right? So that's why we have this common frequency. Actually, I'm not sure whether some of you noticed, right? The other common one is 44.1 kilohertz, right? Yeah, some of you know it. So 44.1 kilohertz is also a standard for our the sampling for the voice. And 48 kilohertz is the other one. Okay. So it's about 2 times, right? Slightly more than 2 times, right, of your actual frequency for your voice. Okay. So now the question you may ask is, let's say you have a signal, right, but your sampling rate is less than the Shannon. If it's less than what Shannon sampling theorem tells you, what happens, right? So let's say if you look at your signal like this one, right? your signal frequency actually is more than 50 Hz, right? So actually it's more than 50 Hz, right? So you can see there is something right above 50 Hz. Now, if this signal, right, you sampling at 100 Hz, let's say. So what happens is you will have this problem called aliasing. So if this kind of signal, right, is sampled at 100 kHz, right? So if you look at the spectrum, right, you will see an aliasing problem here. This one, I think is an important topic for electrical engineering. For you, I think you just need to have a basic idea here. And how can we avoid the aliasing problem? Right? One way we can do is we can use a filter. So basically, first we limit the frequency range. Right? For example, for this case, right? For just now the case, right? Just now the signal we have some components, right, which is above 50 Hz, right? So if you have a low pass filter, so first you filter out all the frequencies above, let's say 40 Hz, right? So you filter out all the frequencies above 40 Hz, right? So now you don't see anything above 50 Hz in this case, right? Now, if you sample this signal at 100 Hz, right, then we'll be fine. Because now you don't see any aliasing here. Okay. So to avoid the aliasing, right, one way is you can use filter, anti-aliasing filter. Okay. So in many applications, right, anti-aliasing filter are not required. It really depends on the application. Right? If it's the signal actually if it's from temperature sensor, right? So the frequency actually is pretty low. Temperature sensor thing. Yeah. So you don't need those anti-aliasing filter. But if it's from the voice, whatever, for example, so it depends. Okay, so quantization error, we have discussed a little bit earlier, right? So basically, for digital signals, right, the problem is you have a limited number of symbols, digits, right, to represent the analog signals. So that gives you some error, right? Because for any digital signal, right, it can be 10 bits, it can be 12 bits, or 16 bits, right? Again, for whatever it is, right, you have a limited number of bits to represent the analog signals, right? So there is a quantization error for this case, right? So the important thing is, for many applications, right, the important thing is you need to decide whether this quantization error is serious. Right? If your data can be represented by 8 bits, right? You say, okay, this is sufficient for my applications, then that's fine. Okay. Okay, so this is the sum of quantization error we discussed, right? So if your inputs, right, analog scale is from 0 to 1. Okay. So for this case, if you say so you use the 3 bits to represent the analog signal, right? So you only have 8 possible values, right? Okay, 8 possible values. So your analog signal, if it's so analog signal is any value in between 0 and 1, right? So it's a straight line, right? So your digital signal now actually is like a step line, because you only have 8 possible values. Right? So if you compare the analog signal and the digital signal, right, yeah, you will have this error, right? Okay? And the resolution we talk about basically is 1 over 2 to the power of n, right? So for this case, my resolution here actually is only 0.125 because you use 8 possible values, right? 8 digital values to represent the analog scales from 0 to 1. Okay. So other possible error sources in ADC, it could be the linearity, right? Because what is linearity? Basically, it's inside the ADC, right? Usually you have some amplifier. Right? So this amplifier basically is going to amplify your signal. Okay. And not all the signals can be amplified by the same constant. Right? So that introduces the linearity error. And also the offset error, right? That offset error, I think is the usual, right? Basically, let's say you use a weighing scale, right? Every time you need to check first whether the starting is 0. Right? Yeah? Your weighing machine, right? So if you take your weight, right? Every time, the first thing you need to check whether it's 0, right? Otherwise, the reading is not accurate. So this is the same thing. So you need to check whether there is an offset error. And this is what we call offset error. And the other one is inaccurate reference voltage, right? Yeah. So, for example, like in a circuit, right? Usually we take the reference voltage, for example, like from 3.3 volts, right? But actually, if you take the reference voltage from the power supply, right, actually it's not accurate. Why is that? Because let's say you use batteries, right? You use 2 batteries. The battery voltage actually is not always 3.3 volts. It depends on, because as you use more, right? The new battery and the old battery, right? The voltage actually is slightly different. It's not always 3.3. So if you need the accurate reference voltage, then you need to have a special circuit. And of course, I mean the noise also affects the accuracy, the noise. Okay, so this is what we have discussed for the signals, right? So if you have input signals, right, we need to do some signal conditioning, like using the anti-aliasing filter, right? Basically, you need to limit your frequency range. Then you have analog to digital converters. Right? So for the analog to digital converters, you need some reference voltage. Okay. Then the output from the analog to digital converter, right, it will go to the microcontrollers to do the processing. Okay. So the signal conditioning we have discussed for the Vin, right? For the analog inputs, right? For the inputs, actually, it can be anything, right? It can be anything, right? But in order for the ADC to process it, right, we have to limit the range. Right? We have to limit the range to 0 to 8 dB. Okay. Okay, this is one of the signal conditioning we need to do. Do you agree? And okay, next I want to show you a little bit, right? How can we do analog to digital conversion? Actually, there are many ways to do that. For the analog to digital conversion, at least there are 5 to 6 ways to do it. So I want to show you one most common one is called successive approximation methods. Right? So what it does is, let me give you the basic idea. Okay. So you know, for ADC, the range is from 0 to VDD, right? Okay. Now let's say you have an input voltage here. somewhere here. Okay.
Okay.
So how can we generate the digital output, right? For the successive approximation methods, right? The easiest way is first you compare with the half VDD. Okay. Half VDD, right? So now if you check, if you compare VD and half VDD, right? For this case now it's below half VDD, right? So that means my first peak is 0, right? Because it's below. Okay. So when it's 0, now you know V in, right, is somewhere in between 0 to VDD, right? So now you need to check with quarter VDD, yeah? Okay. So now if you compare V in and quarter VDD, right? V in is higher, right? So that means my second bit is 1, right? Okay? So if your second bit is 1, you know your V in is somewhere in between quarter VDD and half VDD. Right? Okay? So now you check again the mid level of between the quarter VDD and half VDD, which is what? Is this one 3/8 VDD, right? This level. Okay? So if you compare this 3/8 VDD to V in, right? V in is below, right? Correct? That means my third bit is 0, right? So that means your V in is somewhere between 3/8 VDD to quarter VDD, right? So, and so on, and so on. Right? You can compare with the more levels in between here. Right? You can have more bits. So in this way, actually, you can generate the digital output. So now your V in is your analog input, right? This is your digital output, right? Yeah. So in this way, the ADC, right? You are performing your ADC function, analog to digital conversion. Yeah, agree? Sounds possible, right? Every time you click, you compare the mid level of your range. Okay. So yeah, this is sorry. Yeah, so here it shows the same thing as I explained to you just now. So actually from the name here, right, it's what successive approximation. So basically you need to compare to the different levels, right, successively. So then you can come up with the result. Okay. So you can go through the step here. Yeah. So it's similar. Right? The first one, the first step you compare with half VDD, right? So because now V here is below, right? So your first bit is 0. Then you compare with the quarter VDD here, right? Yeah. Now because the V is above, right? So your bit is 1. Right? Then you compare with the 3/4, yeah. Sorry, 3/8 VDD. Yeah. So on. Okay. Okay, so again, this is not I don't think you need to concern how to implement this successive approximation. So this is the topic for again for chemical engineering. How to implement the successive approximation. Okay, so the summary for the successive approximation, right? Basically, the comparison it will produce 1 bit by 1 bit. Okay, for each comparison, right, it will produce 1 bit, right? And it's starting from the most significant bit. MSB. Okay. You know what is the most significant bit? Let's say you have 4 bits, right? 1010, right? The most significant bit is the leftmost bit. Yeah. This significant bit is the last bit. 1010 is the rightmost bit. The least significant bit. Okay, let me come back to the. So we have discussed again here, right, the key components here, right? So signal conditioning, analog to digital converters, and to the microcontrollers, right? Okay, so this one we have seen before. Right? Okay, so for the ADC modules in the Arduino, right? So do you still remember? In the Arduino, right, we actually use this SAM3X microprocessor, right? So inside this chip, we have these ADC modules. Okay, ADC modules, and these ADC modules, they can be 10 bit or 12 bits. Depends on your. You can actually select to be 10 bits or 12 bits ADC. Okay? So the conversion rate is about 1 meg plus. Right? Again, this is programmable. Right? And you can use the external reference voltage. Right? Okay? And the rest of the functions, I don't think it's very important to you. Okay, so the structure here again, I don't discuss further, right? This one, you can use it as a reference if you need data. So no need for me to discuss in detail this page. Yeah, the conversion sequence also not very important. Okay. Okay, so for the Arduino Duo, right? Yeah. We have the 12 ADC channels available, right? So the default resolution is 10 bit. So 10 bit basically corresponds to 1024 levels. This one you know, right? Why 10 bits is 1024 level? Basically it's 2 to the power 10, right? Yeah. So if it's 12 bit, right? Because you can change it to a 12 bit. If it's 12 bit, actually it's 4096 levels, right? 2 to the power 12. Okay? And the analog reference voltage actually is 3.3 volts. You cannot change it. And how do you use the ADC? Actually, it's very simple, right? In the Arduino board, right? I think some of you see it before.
The Arduino board.
So the Arduino board here. Here, 1, 2, 3, 4, 5, right? Basically, it's the digital I/O, right? And here, actually, you can see A1, A2, A3, A4, right? Yeah, that's the analog I/O. Analog I/O. So you can use these pins, right, to feed in your analog inputs and produce your analog outputs. Okay, and the functions, right? Last time you used these functions called a digital read, right? Correct? And digital write, right? These two functions, right? Digital read and digital write. And to control the analog pins, right? You can actually use analog read functions, right? To read the values from the analog pins. So be careful, right? So if you want to use the analog pins, right, you need to use a different functions for that. Okay, so I think we are done today. Yeah.